Hello and welcome to my second course dedicated to feedback amplifier analysis using the Middlebrook approach. This topic deserves special attention because the analytical steps in the Middlebrook approach naturally follow the intuitive objectives of applying a feedback connection to an open-loop amplifier and at the same time account for the incidental or unintentional feed-forward paths. Dr. Middlebrook used the term low entropy for any formula that was meaningful and made sense. In the same spirit, I would like to characterize Middlebrook's treatment of feedback amplifiers as low entropy formulation of U.S. Patent 2102671 filed by Harold Black in 1937. Now, even though Black is credited for inventing negative electronic feedback, the concept of negative feedback dates back at least to the days of the steam engine. This course is based on Chapter 5 of my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online from any bookseller. I will first start with the basic feedback block diagram, discuss its limitations, followed by the proper formulation of electronic feedback, gain analysis using the Extra Element Theorem for dependent sources. I will then work out two examples in this video, a two-stage voltage sense current feedback amplifier and a two-stage current sense current feedback amplifier. In the next video, I will work out two more examples, a three-stage voltage sense voltage feedback amplifier and a two-stage current sense voltage feedback amplifier. We begin with the basic block diagram and the feedback formula. This is the block diagram used almost universally to introduce the concept of feedback, and it can be found in all electronic textbooks. It is easily understood and well appreciated. G is the main plant or transducer, which is a relatively complex system and has large variability. That is to say, the value of G can have a wide range from G min to G max. G is also referred to as the open loop gain. H is the feedback connection and is a much simpler structure in comparison to the main plant and can be made to have as little variability as desired. This here is the differencing node where a small part of the output signal attenuated by a factor H is subtracted from the input signal and applied to the main plant. Now, in a few lines of algebra, we can easily show that the gain of this system, AF, output over input, is given by G over 1 plus GH. AF is also referred to as the closed loop gain. This is then the basic feedback formula. Now let us look at the benefits of feedback. The first motivation behind the use of feedback follows from the fact that G, the main plant, has large variability, and as such, it cannot possibly be used to produce an output signal with any amplitude fidelity. That is to say, the output signal will be all over the place regardless of what the input signal is doing. But we realize that since H has very little variability, then if we were to make the product H times G min much larger than unity, then the closed loop gain AF would effectively reduce to 1 over H. Recognize that our feedback formula was G over 1 plus GH, and if we multiply up and down by H and make the product GH always much larger than unity, then GH over 1 plus GH is effectively 1, and the closed loop gain AF effectively reduces to 1 over H. Now, since H is an attenuation, 1 over H is a gain, and if H has very little variability, AF will have very little variability. That tells us that the way we would choose the attenuation H is to make it equal to the reciprocal of the desired gain AF. And that's it. We apply feedback H in order to make the closed loop gain independent of the variability in G. The second motivation behind the use of feedback follows from its ability to reject spurious external signals injected into the system as shown here. Using superposition, we can easily show that the output signal is given by the input signal multiplied by the feedback gain, as we showed in the previous slide, plus the spurious signal divided by 1 plus GH. Now, since in a feedback system we make GH much larger than unity, then the output signal approximates as follows. It is the input signal times 1 over H plus the spurious signal divided by GH. And if we factor out 1 over H, we see that the spurious signal is added to the input signal attenuated by a factor G. So if G is large, the spurious signal divided by G is hopefully much less than the input signal, so that the output signal is essentially given by the input signal divided by H. We can now define some basic terms of noise analysis. We showed that the output voltage is given by the superposition of the input signal multiplied by the feedback gain and the spurious signal divided by 1 plus GH. So when we look at the output, we see two components in there, a signal component and what we call a noise component. We can then define a signal gain, which is the ratio of the signal component in the output to the applied input signal, and naturally that's going to turn out to be the feedback gain itself. And we can also define the noise rejection, which is the ratio of the noise component in the output to the spurious signal applied in the system. Now we can define the ratio of these two as the noise rejection ratio, and that turns out to be equal to G. And really what that tells us is that any spurious signal injected in a feedback system is effectively rejected by the amount of gain that precedes it. So if you were to imagine that G comprises two main plants, G1 and G2 in tandem, and the spurious signal is applied between the two, then the noise rejection ratio is going to turn out to be equal to G1, the amount of gain that precedes the spurious signal added to the system. Now, the power supply rejection ratio of an amplifier or a linear regulator are the most common examples of noise rejection ratio shown here. A third benefit for using feedback is its ability to fight distortion generated by nonlinearities in the main gain stage G. This follows directly from the ability of feedback to reject spurious signals, as we're going to show next. Any nonlinearity in G causes amplitude distortion, which produces harmonics at the output of G. These harmonics, in turn, are treated as spurious signals which are rejected by the feedback loop. Here's a block diagram showing that. These two together form the plant with some nonlinearity. It's separated into its linear part and nonlinear part, represented by this little hysteresis. Now, the nonlinearity will generate harmonics at the output here, and these harmonics can be treated as spurious signals being injected into the system. And the feedback loop will reject all of these harmonics as spurious signals. And this is how feedback will fight distortion in the main plant G. Only one note of caution here. This separation of a nonlinear plant into a linear and nonlinear part is a little tricky and slightly involved, but we don't have to be concerned about that in this course. We are now going to look at the limitations of the feedback block diagram, which turned out to be so very useful to the understanding of the principles and properties of feedback systems. That feedback block diagram is, however, useless in the analysis of electronic feedback circuits, mainly because the feedback network loads the input and output circuits of an amplifier. When blocks are interconnected, they don't load each other down, and each block retains its own characteristics. Second, the feedback network is bilateral and has a finite forward gain in addition to the gain of the amplifier. Third, block diagrams in general bear no resemblance to any circuit, and the feedback block diagram is no exception to that. It takes quite a bit of useless effort to force a feedback circuit into the feedback block diagram in order to figure out the individual gains G and H. The fact is that G and H are intermediate results which should be of no concern to us at all. Really, I mean it. So instead, we're going to formulate the concept of feedback directly, as stated by its inventor Harold Black, using the Extra Element Theorem for dependent sources, as Dr. Middlebrook showed in his paper, Design-Oriented Analysis of Feedback Amplifiers, which appeared in the proceedings of the National Electronics Conference in October 1964. In his patent application, Black wrote, "The elements of a system with feedback are an amplifying element having an input and an output, and a coupling or path for returning some of the output wave to the input of the amplifying element." The key words here are an amplifying element and a return path from the output back to the input. And it is precisely this idea that we are going to formulate directly using the EET for dependent sources. The result will be a more natural formulation of electronic feedback than the well-known feedback block diagram found in all electronic books. We are now going to see that we do not need to be concerned with the details of the amplifying and feedback paths. That doesn't mean that we're going to ignore parts of the circuit, not at all. All I'm saying is that we do not have to stress determining and identifying G and H of the feedback block diagram inside our electronic feedback circuit. If you don't believe me, here's an electronic feedback circuit. Can you see G and H distinctly from each other? You can see the amplifying path this way from Q1 to Q2. You can see the input, and you can see a feedback connection. But a G and H distinct from each other is not readily discernible. And the only reason for that is the feedback path and the amplifier, they load each other down, meaning the feedback path slightly modifies the gain in the forward path of the amplifier, and the amplifier itself slightly modifies the amount of feedback taking place inside this circuit. And it is a total waste of time, in my opinion, to try and separate the two. It can be done. It is done in all your textbooks. But that's a waste of time trying to separate those two from each other and determine a G and H and apply the feedback formula, G over 1 plus GH, to get the closed loop gain. Let me show you what we can do instead, a much simpler way. Here's a feedback electronic circuit. We're going to take it easy. In it, I can identify some amplifying path going from the input to the output, just like Harold Black mentioned in his patent. For a feedback amplifying system, you need an amplifying element between an input and an output. And here it is. The details of that path are of no concern to me. We don't need to know it. I can also identify some connection between the output back to the input, a feedback path that returns part of the output signal back to the input, just like Harold Black mentioned in his feedback patent application. The details of that path are not necessary at all. And for this system, I can write a gain output over input, which I will call the closed loop gain, only because in it I can imagine the feedback connection removed and the amplifier operating just all by itself, and that would be the open loop gain. And if I make a feedback connection, I will call the gain now, in distinction to the open loop gain, as closed loop gain. Nevertheless, it is just a gain. Now, before we go further analyzing this circuit, as you look at it, wouldn't you want this amplifying element A, which can be a transistor, a FET, a vacuum tube, wouldn't you want its gain to be infinite? Yeah, you can want it, but you know you can't get it. But wouldn't you want it to be large? In fact, if you don't have any large gain here, A, you have no feedback circuit. You just have a circuit. But for this to be a feedback electronic circuit, A has to be large, and ideally it's got to be infinite. And in that case, when it's infinite, your closed loop gain, the gain of this system, will be dictated by the feedback network, which is what you do in all your ideal op-amp circuits. So you're quite familiar with the idea that it would be a wonderful thing if this A was very, very large and ideally infinite. And let's see how we can exploit that to get to the feedback formula, the natural feedback formula, the one that's given by Dr. Middlebrook. Now that we appreciate the importance of the amplifying element A inside the electronic feedback circuit, we designate it as the extra element and apply the extra element theorem for dependent sources as shown. AF is the closed loop gain. It is equal to the closed loop gain with A equals to infinity, also known as the ideal closed loop gain. It is followed by a correction factor as shown here. The ideal closed loop gain is in fact our design goal. It is our design objective. In real life, we don't have infinite gain amplifiers, and the closest thing that we can get to one is an op-amp. So why don't you think of your first op-amp circuit that you learned? A resistor R2 connected from the output to the inverting terminal, and another resistor R1 connected from the inverting terminal to an input source Vin, with the non-inverting terminal grounded. You learned the gain of that circuit was minus R2 over R1, and the gain of the op-amp never got into the picture because you assumed it was infinite. But the gain is never infinite, and this is the correction factor that accompanies the ideal closed loop gain. In the numerator, script A bar is the null inverse gain with respect to A, the amplifying element, with the response nulled, and in the denominator, A bar is the inverse gain with respect to A, the amplifying element, with the excitation set equal to 0. And this is all you need to know for gain analysis of feedback amplifier. This is the feedback formula for gain analysis of electronic feedback circuits. That's it. Nothing else. Let us now look at the individual components of the feedback formula given by the extra element theorem. First, let's look at the ideal closed loop gain, in which we let A go to infinity. So when we let A go to infinity, U1 will shrink to 0. So if A represents, let's say, the beta of a transistor, beta IB of a transistor, then if beta goes to infinity, the base current that it depends on will shrink to 0. If this is the transconductance of a transistor, say Gm V pi, where V pi is the base to emitter voltage, and you let Gm go to infinity, then V pi will shrink to 0. And that's how you determine the ideal closed loop gain. Next, we determine the inverse gain with respect to A with the excitation set equal to 0. In this case, we inject at U2 a signal we call minus UT, and we set the input excitation equal to 0, and we determine how much U1 is generated by the signal being injected at that point where U2 is. So if U2 turned out to be a dependent current source, then U minus UT really represent an independent current source at that point, pointing in the opposite direction. Likewise, if this was a dependent voltage source, then this would be an independent voltage source pointing in the opposite direction at that point, U2. Finally, we look at the null inverse gain. In this case, we retain the input so that the injected signal and the input signal, or the excitation of that transfer function that we're looking for, together they null the response. And you determine how much U1 is generated by UT, and that ratio is given by the null inverse gain. And that's it for the gain analysis of feedback amplifiers. This is all you need to know, and these are the three components of it, and that's it. We are now going to determine the midband voltage gain of this two-stage feedback amplifier. In the midband region, CS and CE1 are short circuits. This type of feedback is referred to as voltage sense and current feedback, or voltage sampling and current mixing. Now, since this is an amplifier, the input voltage is expected to be much smaller than the output voltage, so that the voltage across RF, the feedback resistor, is approximately the output voltage. That means we are effectively sensing the output voltage and feeding back a small current signal with a gain 1 over RF, and that current is being subtracted from the input current signal at this node here. So this is the differencing node of this feedback amplifier. And the difference of these two currents flows through the main amplifying path. We do not need at this point to know the details of these paths, because the feedback formula will catch all that. So now we are going to replace Q1 and Q2 with their low-frequency equivalent circuit model, or the beta model of the transistor. And now, with these two transistors replaced with their equivalent circuit model and the two capacitors short and VCC set to ground, we obtain the equivalent circuit model of this feedback amplifier. RB here is the parallel combination of these two bias resistors, R1 parallel R2. So this is the circuit that we are going to analyze. In this equivalent circuit, we see that the gain in the forward path comes from beta 1. The second stage here is configured as a follower, so that doesn't contribute to the gain of the output voltage. So we designate beta 1 as the extra element and apply the extra element theorem for dependent sources to beta 1. That's given here. So what we have to determine now is the voltage gain with beta infinity. Then we'll determine the null inverse gain with respect to beta 1 with the output nulled, and the inverse gain with respect to beta 1 with the input set equal to 0. To determine AV infinity, we said we're going to let beta 1 go to infinity. When beta 1 goes to infinity, IB1 will shrink to 0, and the voltage drop across R pi 1 will shrink to 0. But that voltage is the same as the voltage across RB, and hence, when beta 1 goes to infinity, this node here goes down to ground potential, and there will be no current flow neither through R pi 1 nor through RB. That will make this current I here equal to 0. What that means is that the entire input current at this junction will turn around and flow through the feedback path, since there is no current going this direction. This current IN in turn is given by Vin divided by Rs, since this node here is at ground potential and Vin appears directly across Rs. So that current IN is Vin divided by Rs. And as that current flows through the feedback path, it creates a voltage drop across RF given by Vin over Rs times Rf. Moving on to the output node, we see that V0 also appears across RF, since this node here is at ground potential, or virtual ground, and this node here is sitting at the output voltage. And what that means is that the output voltage is equal to the negative of minus V in over RS times RF. Let us write all that down. Beta 1 goes to infinity, IB1 goes to 0, which means that V pi 1 goes to 0, which means that this current goes to 0. The input current, which is given by V over RS, flows entirely through the feedback path and creates a voltage drop across RF V in over RS times RF, which is equal to the negative of the output voltage V naught. And from this last step, we obtain the ideal closed loop gain equal to minus RF over RS. Now we determine the inverse gain with respect to beta 1 with the excitation set equal to 0. To do so, we replace the dependent current source with an independent current source pointing in the opposite direction and determine the ratio of IB1 to IT. To do so, we'll first do a Norton equivalent resistance looking into RB, and that is given by first setting the independent excitation equal to 0 and recognizing that what we have now is RS in parallel with RB followed by RF in series with RL in parallel with the resistance looking back into the emitter of the second amplifier. But that one is the total resistance in the base of that second stage amplifier divided by 1 plus beta 2. And that gives us the Norton resistance looking back in here. It is RB parallel RS, this in parallel with that one, in parallel with everything else from here looking onwards, and that's going to be RF first, plus everything that we see looking from that point to the right, but that's going to be RL and everything else looking back into the emitter of the second stage, which is R pi 2 plus RC divided by 1 plus beta 2. And that gives you the Norton resistance looking back into this circuit here. We now determine the Norton equivalent current source looking back into the network, which is the short circuit current at this point, and that is seen to be given by the successive current division of IT by two current dividers. Well, the first current divider is going to be between RC and the resistance seen at this point, which is going to be R pi 2 plus the reflected emitter resistance, which is 1 plus beta 2 RL parallel RF, and that is shown here. It's RC divided by RC plus R pi 2 plus 1 plus beta 2 RL parallel RF. Now, when we multiply the current IB2 by 1 plus beta 2, we get the emitter current, and that is divided between RL and RF to give the Norton equivalent current. So we write that second current division, and from this we get the amount of Norton current in terms of the current source IT given by this expression, which follows from this one by multiplying up and down by RF. This turns into RL parallel RF, and we can divide the whole expression up and down by 1 plus beta 2 RL parallel RF, and we get here RC over RF. Now, with the equivalent Norton current source and the Norton resistance, we can now find the ratio of IB1 to IN, and that's given by this current division, which is equal to this expression here. In this expression, we need to substitute the value of the Norton resistance. So in our final substitution, we substitute the value of Rn that we had determined for the Norton resistance in this expression, and we get the ratio of IB1 to IT, or the inverse gain with respect to beta, with the input shorted. That's our inverse gain, beta 1. And finally, we determine the null inverse gain with respect to beta 1. In this case, IT and Vin together are going to null the response V0, and that will go to 0. Now, if the output voltage goes to 0, as you can see in this diagram, the voltage across RF is going to be the voltage across R pi 1. The voltage between this point and ground is the same as the voltage between this point and ground. This is virtual ground. So this voltage drop here, IB1 times R pi 1, appears across RF. That's one result. Another result is that if I null the output voltage there, then the entire emitter current is going to go and flow this way into the feedback path under these null conditions. Now, this current that's going to flow according to this expression that we got earlier is going to be IB1 R pi 1 divided by RF. But we said this current is going to be also the same as this current here, which is 1 plus beta 2 IB2. And IB2 itself is going to be the current division of IT between RC and R pi 2 when this node here is at ground potential. That is a simple current division. So IB2 is given by IT times RC over RC plus R pi 2, that's IB2. And when we multiply that by 1 plus beta 2, we get the emitter current, and that's equal to the negative of the current flowing in this direction. So if I find IB2 here, multiply it by 1 plus beta 2, it's equal to negative of IB1 R pi 1 over RF. And that means that I can now solve for IB2 to IT with the response nulled from this expression here. And we get this. And we're done as far as the three components of the extra element theorem with respect to beta 1 is concerned, which is the feedback formula. And when we substitute these results in the feedback formula given by the EET, we obtain the complete expression of the voltage gain of this feedback amplifier system. Up front, we have the ideal closed-loop gain, which corresponds to the gain of the amplifier system when beta 1 is infinite, and this is the correction factor owing to the fact that beta 1 is not infinite. Now, there's a minus sign here, and you're wondering where that comes from and whether that has any significance or not. Indeed, it does. Well, let's look at this expression first by letting beta 1 go to 0. We know when beta 1 goes to infinity, this expression is a negative expression given by minus RF over RS. What happens if beta 1 goes to 0? Well, multiply up and down by beta 1 and let beta 1 go to 0. In the numerator, you are left with this negative term here. In the denominator, you're left with this positive term here. Now, the negative term in the numerator and this negative term multiply each other out to yield a positive expression for the gain AVF. Now, what that means is that as beta 1 goes from infinity to 0, the sign of AVF changes from negative to positive. With beta infinite, we have a negative gain actually, given by minus RF over RS. When beta 1 goes to 0, the gain becomes positive. However, that is not even a gain, that turns out to be an attenuation. Now let us see if we can see all this on the circuit diagram itself. Okay, so if we let beta 1 go to 0 in this picture here, then there is no longer a path of the signal through the amplifier to the output. The only path that we have from the signal, from the input signal to the output, is through the feedback connection. So if there's nothing going on here, and the signal goes from the input to the output through the feedback path here, through the feedback connection, I should say, then all I have is a bunch of resistive dividers, voltage dividers, and that's a non-inverting path. The output voltage sign follows that of the input, and it is an attenuation. There is no gain in the system. We killed the amplifier. Now, if the gain of the amplifier becomes very large, then the dominant path of the signal from input to the output is through the main amplifier path, and its gain is controlled by the feedback connection. That's when you have feedback. You have feedback action when you have large gain in your amplifier around which you're applying the feedback. The feedback action dies when the gain of the amplifier goes to 0 or very low. The feedback connection nevertheless is there, but it can no longer be called feedback. As you can see, if you let beta 1 go to 0, there's nothing going on up here as far as gain is concerned, and all you have is a resistive division between the input voltage and the output signal, which is an attenuation. That's why that gain sometimes is referred to as the gain of the amplifier without the action of the feedback, but with the loading of the feedback. And without the action of the feedback means that you kill the gain of the amplifier. So on the circuit diagram, we can quite clearly see why, when beta 1 is 0, that the gain from output to input, which is an attenuation, it's a positive number. And that when beta 1 is very large, the amplifier is strong, and feedback action is taking place, the gain is inverting. It's essentially minus RF over RS. And that is what explains the presence of this negative sign here. To summarize then, we have two paths from the input to the output. The first path is through the inverting amplifier, and the second path is through the feedback connection. When the gain of the inverting amplifier is large, ideally infinite, then the dominant path clearly is through the inverting amplifier, and the feedback network only controls the value of that gain, minus RF over RS. And it's an inverting gain. When we kill the gain of the amplifier, make beta 1 all the way go down to 0, then the path, the inverting path, dies out, and the only path left for the input signal to reach the output is through the feedback connection, which is a non-inverting path. And the gain through that path is nothing more than an attenuation given by the voltage division that you get from the resistive connections that you have. And the beauty of all this is that it all comes out naturally out of the feedback formula given by the extra element theorem for the gain of the amplifying element. And you get the result like this, in very meaningful form. And you don't have to stress over determining the G block and the H block of the feedback block diagram and trying to force this amplifier into that block diagram in order to be able to determine the closed loop gain AVF. As I said, it all comes out naturally out of the feedback formula given by the extra element theorem for the amplifying element inside the forward path of the signal. We're now going to determine the transconductance of the feedback amplifier circuit shown here, which is essentially the same circuit as before, except that this time we are going to be feeding back a signal proportional to the signal current in the collector of Q2 rather than the signal voltage at the emitter of Q2. This output stage Q2 is now biased by the resistor RE2 at the quiescent current, which is bypassed under signal conditions by CE2. RE, shown here, is a current sense resistor, which is much, much smaller than RE2, as well as much smaller than the resistance looking back into the feedback network RF. So what RE does really is creates a voltage drop across it that's proportional to the emitter current, which, if the transistor beta is large, is the same as the transistor collector current. So effectively what we're doing, again, is to sense this current I0, feed it back, and make it follow an input voltage Vin, regardless of the variations in the load RL. Hence, what we want to solve for is the closed-loop transconductance IO over Vin. This is what we're trying to solve for this feedback system. It's known as current sensing and current feedback. Here's then the small signal equivalent circuit model of our feedback amplifier. Very much the same as the one before. And this is the feedback gain formula for the closed-loop transconductance. It is the ideal closed-loop transconductance with beta 1 equal to infinity, followed by a correction factor in which script beta 1 is the null inverse gain with respect to beta 1. In this case, the response is not the emitter voltage that is being nulled, but it is the collector current of Q2 that's being nulled. And in the denominator, we have the inverse gain with respect to beta 1 with the excitation set equal to 0. So really, essentially, most of our calculations are the same as before in the previous example. Now you might ask, why didn't I pick up beta 2 as my amplifying element, which goes to infinity? Well, the reason is quite clear, is because when I make beta 1 go to infinity, the current gain from this point to that point goes to infinity. But if I make beta 2 go to infinity, the current gain from IB2 to beta 2 doesn't go to infinity because of the presence of the emitter resistance, or all the resistance connected to the emitter circuit, which involves RE and the feedback resistor RF, but which is mostly dominated with little RE here. And that's why we chose beta 1. And that's important to note. Now you can choose beta 2 to be infinite. You will not get any wrong results, but you don't get the term that's appearing up front, the ideal closed loop gain that you would like it to be. We are now going to determine the ideal closed loop transconductance with beta 1 infinity, and we do that on the circuit diagram. This is mostly a review. Beta 1 goes to infinity, IB1 goes to 0. That makes the voltage V pi 1. That is the voltage that appears across RB, and R pi 1 go to 0. That makes this current go to 0. As a result, the input current flows through the feedback path, and that current is given by Vin divided by RS, because this is virtual ground here, and the voltage across RS is Vin. So that current is Vin over RS. And as that current flows through RF, it will create a voltage drop across it, which is really the same as the voltage drop that appears across RE in this polarity, because this node of RE is connected to this node of RF. The other side of RE is ground, and the other side of RF is virtual ground. So let us write all that down again, summarize that. Beta 1 goes to infinity, IB1 goes to 0, V pi 1 goes to 0, that current goes to 0. The input current flows through the feedback path, and the voltage it creates across the feedback resistor is the same as the voltage across RE, the sampled voltage. And that current is going to be Vin over RS, in this case here flowing through RF. So when that happens, there's going to be a current in the branch RE, and the sum of that current and the sum of this current is going to be equal to IE2. But IE2 is related to the output current, we said, by the alpha of the transistor. The alpha of the transistor is beta over 1 plus beta of the transistor, which is nearly unity. And that means also simply that the emitter current is nearly the same as the collector current. Well, the emitter current itself is itself the feedback current plus the current through the emitter resistor Re. Each one of these, we know the feedback current is minus Vin over Rs, and the emitter current is going to be minus Vin over Rs times Rf, that voltage there, which appears here, divided by Re. Factor out Vin, and from there we can determine the ideal closed loop transconductance with beta 1 infinity. Next, we determine the inverse gain with respect to beta with the excitation set equal to 0, as shown here. This is exactly the same calculation as before, so we have this result already. So third, we're going to determine the null inverse gain with respect to beta 1 with the response null. In this case, the response is the output current here, which is the current of the Q2. Beta 2 IB2 is going to be null and made equal to 0. Well, if that's 0, and since beta 2 is not 0, that means that IB2 is 0. And if IB2 is 0, there is no current flowing in this branch. The voltage across R2 is 0. Not only that, but the current IT flows entirely through RC, creating a voltage drop IT-RC across it. And when this voltage here is 0, the voltage across R2, that IT-RC appears across the current sense resistor. And it starts a current through it, which flows entirely through RF because there is no emitter current. Remember, you nulled the output current, the collector current. And in this model, if you nulled the collector current, that means you nulled the base current. That means you nulled also at the same time the emitter current. So all the current that is flowing through Re is actually flowing through RF. And we have a voltage drop now across RF, which is IT-RC divided by Re times RF. The sum of the voltage across RF and Re is actually the voltage from this node to ground. And that's the voltage across R1. So if I divide the sum of these two voltages by R1, I'll get IB1, and I should be able to determine my null inverse gain that way. Let us write that down. IB1 is going to be the sum of those two voltages, the voltage across the current sense resistor, IT-RC, plus the voltage across the feedback resistor under these null conditions, which is IT-RC divided by Re times Rf. The sum of those two divided by R1 is going to give me the current IB1. So now I can determine the null inverse gain by dividing out by IT, and that's going to be 1 plus Rf over Re into Rc over R1. And finally, when we substitute our results in the feedback formula for the transconductance given by the extra element theorem, we get the expression for the closed-loop transconductance. This is the ideal closed-loop transconductance, which we discussed earlier. This is the correction factor, in which if we let beta 1 go to infinity, we recover our ideal closed-loop transconductance. We also notice that the sign here is positive as opposed to the previous example in which it was negative. And the reason for that is, in this case, the signal path from the input to the output current is non-inverting both through the amplifying path as well as through the feedback path. In the amplifying path, you have two common emitters in cascade, each one being inverting results in a non-inverting path. That's why that sign is positive. And if you let beta 1 go to 0 by multiplying up and down by beta 1, you get an attenuation, which is the gain of the feedback amplifier without feedback, but with the loading of the feedback. And all that comes out naturally, as I said, from this feedback formula given by the extra element theorem.